Alright class, so today we're in chapter 5, section 4. I think you're really going to like this section, especially when compared to maybe the past couple of sections. We've been dealing a lot with limits, we've been dealing a lot with Riemann Sums, which is the limit of a sigma notation sum. They're pretty tedious to work with. And in the last section, we defined a Riemann sum as the definite integral from a to b of some function f of x, and we saw that that resulted in the net area between some function f and the x-axis, and between two vertical lines x equals a and x equals b. Now, to find that net area, it was a pretty tedious process. We had to take the sum first of all, and then we had to do a bunch of algebraic manipulation. Then we had to take a limit, and they were pretty tedious. Well, now we have this very important result called the Fundamental Theorem of Calculus. A fundamental theorem of calculus. Anytime you see the fundamental theorem of anything in math class, think very, very important result. This is going to be the most important result we've had maybe the entire class, but certainly in a while. Fundamental Theorem of Calculus. This allows us to find the definite integral in a much easier fashion than we have been doing with the limits. So, by the way, I should mention that our book refers to this as Part 1. Or maybe like the first Fundamental Theorem of Calculus. I'll call it Part 1 and Part 2. Okay, because you notice down here we have the second fundamental theorem of calculus. So we have the first fundamental theorem of calculus and the second fundamental theorem of calculus. They're both closely related. I should mention also that a lot of books, other books, label these vice versa. So a lot of books call what we call Theorem 511 the second fundamental theorem of calculus. Some books call that the first, and some books call this the second. So if you're accustomed to having those labeled in a different manner, that's pretty standard. But since we're going to stick with our book as far as what we refer to as the first and the second fundamental theorem of calculus, I don't think it's really a big deal either way. They're both very important, and which one comes first, who cares? But we'll call this Theorem 5.9 the first fundamental theorem of calculus, or maybe the Fundamental Theorem of Calculus Part 1. Alright, so just to motivate this, I want to show you how we have been, just a quick review, how we have been dealing with a definite integral. So this left-hand side of the equation right here. How have we evaluated a definite integral in the past? So just, like I said, just to motivate this example, I want to go down here and show you how we would, just to review, how we would evaluate a definite integral. For instance, let's look at, let's pick a pretty easy one. Let's look at the definite integral from 1 to 2 of x squared dx. Okay? Now, up until this point, in just a few minutes, I'm going to show you a very quick way to evaluate this definite integral. But up until this point, and still including right now, the only ways, we have two ways possibly to evaluate this definite integral. The first way is to use a Riemann sum. That is to take the limit as you are increasing the number of rectangles that you can either inscribe or circumscribe about this curve, this parabola x squared, on the interval from 1 to 2. Now that's the hard way. It's possible, now I'm not sure about with x squared, but it is possible to use geometry to find the desired area. But with x squared, that's not a regular geometric formula that we're just going to know how to do off the top of our heads. It's a parabola. In fact, this is just a portion of a parabola from 1 to 2. So, if we had like a rectangle or a triangle, or maybe like a semicircle or a quarter circle, we could use geometry, but x squared, a parabola, is not one of those common formulas we know how to deal with. So it looks like we're stuck with evaluating a Riemann sum to find this definite integral. Now this definite integral, x squared, or the integrand x squared, is a non-negative function over its entire domain, but especially over 1 to 2. Since this function x squared is non-negative, we know the definite integral is going to result in area. Area under the curve between x equals 1 and x equals 2. So just a quick picture. Let's see here. We're going to sketch something over here just like this. We would have x squared. I'll just draw half of it. Looks something like this. Now we are only concerned with the interval from 1 to 2. So let's say there's 1 and there's 2. So since the function is non-negative, we are looking for the area under the curve between x equals 1 and x equals 2, those two vertical lines, and we are going to find this shaded area. Again, if the function is non-negative, if x squared is non-negative, and clearly x squared is non-negative, the definite integral will result in area. Now, how do we go about doing this? Well, recall the definite integral, according to Riemann Sum, was defined as the limit as n goes to infinity of the sum I equals 1 to n of the f at c sub i's times delta x sub i's. Now I think we can forget about indexing the delta x's because for our purposes here we can just let all of the delta x's be of equal width. That is, we can let all the rectangles be of equal width. So I won't index the delta x's, but for a Riemann sum, that's not necessary. Now, what are these things over here? Remember, a delta x, that's the width of every rectangle, and we had a way to figure that out. Delta x was always given by b minus a. So b here is 2. It's the right-hand endpoint of your interval, and a is 1. So 2 minus 1 over n. That's how you find delta x. Now we're not going to let n be any specific number here because we're going to eventually take the limit as n goes to infinity. So delta x we'll just say is 1 over n. Now we also need to talk about the endpoints of our rectangles. These are the c sub i's. C sub i's. Now for a right-hand endpoint, which I would advocate using because they're easier to work with, is always given by a, which in this case is 1, plus delta x, which is 1 over n, times I. Okay? Now we could certainly write that as 1 plus I over n, which I'll do in the next step. So there's my c sub i's, there's my delta x. The last thing to do is to set up this limit. And we can say, I'm going to move over just a little bit, this is the limit as n goes to infinity. Now we have the sum of I equals 1 to n of f of c sub I, so that's 1 plus, we'll say I over n times delta x, which is 1 over n. Okay, so now we have to evaluate this sum, and that's, setting it up is really the hard part. Let's see what we have here. Now we have to evaluate f at that c sub I, but first we can factor out a 1 over n. Remember that we can factor anything, now not out of the limit, but out of the sum, we can factor out anything that does not have an I in it, according to just your typical rules of factoring. So I equals 1 to n. Now, what is f of 1 plus I over n? Well, f is x squared. So it's essentially just 1 plus I over n squared. Because, again, I factored out this 1 over n, and I evaluated f at this c sub I. So now I have to do a little bit of algebra, figure out what this is. I am going to have the limit as n goes to infinity. I still have this 1 over n out front. Don't let that get lost anywhere. Sum I equals 1 to n. Now I just need to FOIL this. Let's see, that is 1 plus, let's see, 2I over n plus I squared over n squared. Okay, again, that's just your typical, multiplying two binomials. We have 1 times 1, then we have 1 times I over n, that gives us 1 I over n. Then we have I over n times 1, so we have two of those things, so 2I over n. Then we have I squared over n squared. Now, just to be clear here, there's like understood parentheses right there and right there, because all of those things are in the sum. And now we can say, all right, that's the limit as n goes to infinity. We still have this 1 over n out front. But now here's what we want to do. We have 1, 2, 3 different terms inside our sum. We can take the sum of each of those terms individually. So we could say the sum from I equals 1 to n of 1 plus the sum of I equals 1 to n. Now, I can factor out, again, anything that's not an I. So let's just put an I there and factor out that 2 over n. And let's go ahead and do the same thing with this last one. It's the sum I equals 1 to n of I squared, and let's factor out that 1 over n squared. So now we have 3 sums. Now, why did I do that? I did that because these are all things that we have memorized by this point. Limit as n goes to infinity. Now we still have that 1 over n out front. Now, what have we memorized that to be? The sum of a constant, in this case 1, from I equals 1 to n, is just n times that constant. So n. Plus, what's the sum? Okay, we have, first of all, we have this 2 over n outside. What's the sum of the i's from 1 to n? Well, we've memorized that to be n times n plus 1 over 2. Plus, we have 1 over n squared times, what have we memorized this to be? We've memorized that to be n times n plus 1 times 2n plus 1 all over 6. Okay, notice this keeps getting longer and longer. All right, now we need to just do a lot of algebra and then just a tiny bit of calculus when we evaluate this limit. All right, so we just have an n first of all. Now let's see if we can do a couple of these in our head maybe. If we need to write some stuff down, we will. Let's think about this. We have n times n and then plus n times 1. So that's n squared over 2. So I can break this apart into 2 different items, 2 fractions. I can have n squared over 2 and n over 2. But then I'm going to multiply that by 2 over n. So I have n squared over 2 times 2 over n. So again, I think that gives me 2n squared over 2n. And then I have that n over 2 times 2 over n. So that gives me 2n over 2n. n over 2 times 2 over n. Okay? Now, again, of course, I haven't simplified anything thus far. Now, I might have to jot some of these notes down. Let's do this. Okay, we have n times n plus 1. That gives us n squared plus n. Then if we multiply by 2n plus 1, that gives us 2n cubed. Then we have n squared plus 2n squared, so plus 3n squared plus n. And that's all over 6. All over 6. We can then break that apart into, let's see, 2n cubed over 6 plus 3n squared over 6 plus n over 6. Okay? Now we have, that's just this fraction right here, but we have it multiplied by 1 over n squared. So let's add an n squared to the bottom of each of those. And so we have 2n cubed over 6n squared plus 3n squared over 6n squared plus n over 6n squared. So I just added an n squared to each denominator. And now lastly, let's multiply everything by this 1 over n, and we get the limit as n goes to infinity. We have n over n plus 2n squared over 2n squared plus 2n over 2n squared plus 2n cubed over 6n cubed plus 3n squared over 6n cubed plus n over 6n cubed. Almost done with this definite integral. You're going to very much so appreciate the fundamental theorem of calculus after it took us so long to do this. Now, taking the limit of all of these things. Now, think about how to take the limit as n goes to infinity, like you're finding the end behavior of a rational function. If the degree of the numerator is equal to the degree of the denominator, then that, finding the end behavior, the horizontal asymptote, is the ratio of leading coefficients. If the degree of the denominator is bigger, then that's not going to happen in this case, so we're not going to worry about that. But if the degree of the denominator is larger, if the degree of the denominator is bigger than the degree of the numerator, then that term goes to 0. So let's see. Where is the degree of the denominator larger than the degree of the numerator? Well, right there. So that goes to 0. That goes to 0. And that goes to 0. Everywhere else, we have the degree of the numerator is equal to the degree of the denominator. So let's see, what are we left with? Well, that reduces to just a 1, a constant. That reduces to 1. And then this reduces to plus 2 over 6. And so what do we have? Well, that's 2 and 2 plus 2 over 6. That's 2 and a third. Okay, 2 and a third. Which equals, I should not write like that. That's what, 7 over 3 reduces to 7 over 3. Now, let me check myself really fast using a calculator. And yes, the definite integral of x squared from 1 to 2 is 7 over 3. So going way back up here where we first started, that shaded portion there, area equals 7/3. Cool. So that took about 15 minutes, but I'm going to show you a way to do it in just a moment where you could take care of this, in maybe a minute, maybe less, maybe a hair more, but it'll go very fast, okay? So we are going to greatly appreciate the fundamental theorem of calculus, because the fundamental theorem of calculus is going to allow us to find definite integrals in a snap compared to this. So this took us about 15 minutes. We're going to be able to do the same thing in a much faster way using the fundamental theorem of calculus. So let's take a look. Here's what the fundamental theorem of calculus says. Fundamental theorem of calculus says that limit that we just took care of, that Riemann sum can be avoided by simply evaluating capital F of B and subtracting off capital F of A. Now recall, what is capital F? Capital F is the antiderivative. So what the fundamental theorem of calculus says, at least part 1, the fundamental theorem of calculus says we need to find the antiderivative, and then simply evaluate the antiderivative at our upper limit of integration and subtract off the antiderivative evaluated at our lower limit of integration. So finding area can be a massive shortcut can be used to find area to simply find the distance between 2 points. Remember, these are two y values. Capital F of B is a y value. Capital F of A is a y value. These are y values on the antiderivative function graph. And if you find the distance between those two y values, that will give you the area under lowercase f of x between A and B. So it's kind of crazy. I'll show you a cool visualization in just a few minutes that I made earlier. But let's look at this exact same example, except with the fundamental theorem of calculus. So let's see here. So there's all of that. So remember that. And let's go up here and show how we would do the exact same thing. We have the definite integral. Actually, I'll go and I'll look at side by side. Actually, let's just look side by side and show how much less the fundamental theorem of calculus, how much less effort it's going to take. So you want to look again at the definite integral from 1 to 2 of x squared dx. Same exact thing that we started with over here, except instead of a limit, we're going to use the fundamental theorem of calculus. Now, the fundamental theorem of calculus says we first have to find the antiderivative. So what's the antiderivative of x squared? Well, I think we all can remember that it's x cubed over 3. If you have a power function like this, you increase the power of your exponent and divide by that new power. Now, here's some new notation for us. Here's the notation we use with the fundamental theorem of calculus. So after we take the antiderivative, but before we have applied the fundamental theorem, we say this. We put it like a half bracket on one side and make sure to put our endpoints. This means we're about to apply the fundamental theorem of calculus. And what does the fundamental theorem say? Because this is capital F. We just took the antiderivative. That is capital F of x, the antiderivative. Okay? And so the fundamental theorem of calculus says evaluate capital F at 2, the upper endpoint. So that would be 2 cubed over 3. That's capital F of 2 minus capital F of 1, which is 1 cubed over 3. Okay, let's clean that up just slightly. And what does this equal? Well, that's 8 over 3, right? Minus 1 over 3. And look familiar? In record time, we get 7 over 3. And what do we have down here? 7 over 3. I think that's a much, much nicer way to evaluate a definite integral. Now, I mean, that is to be not disingenuous. That is a pretty easy antiderivative. You know, sometimes the antiderivatives are hard to find, especially when we get into the next section with substitution. The antiderivatives might be harder to find. And if you have multiple terms, there's sometimes a lot of arithmetic here. But to be clear, there's no comparison in the amount of work it takes to do a Riemann sum versus the amount of work it takes to do a comparable or the exact same definite integral with the fundamental theorem of calculus. So just to recap here, we first find the antiderivative capital F of x. And then we simply take capital F and evaluate it at the upper limit of integration. And then we take capital F and evaluate it at the lower limit of integration. And then we do capital F of B minus capital F of A. And we get the exact same answer that we would get if we did a Riemann sum. The Riemann sum takes a lot longer, and you get the exact same answer. These two things are equal. That's what the fundamental theorem tells us. The fundamental theorem tells us that what we have originally defined as a Riemann sum, the definite integral from a to b of f of x dx, can be found by simply evaluating your antiderivative at b and subtracting off the antiderivative evaluated at a. This is very, very nice. Again, we'll get to much harder examples, but it's going to be super nice to avoid having to do the Riemann sums all of the time. All right, let's look at a couple more examples before we move on to a couple new related topics. Oh, let's see here. Let's look at 1 over x. So let's look at the definite integral. The definite integral from 1 to e of 1 over x dx. Okay? Now, if we were going to do a Riemann sum, this would not be too fun. Because why would it not be fun? Because we would have, when we evaluate f of our endpoints, we would be dealing with a rational function. We have not dealt with any Riemann sums with a rational function. We have only dealt with Riemann sums with like linear, quadratic, perhaps a cubic, and probably a constant function here and there. But it's much more difficult when you start having, a rational function or maybe a transcendental function. Those are much more difficult to deal with. So we're going to really appreciate the fundamental theorem of calculus here. So what does the fundamental theorem tell us to do? The fundamental theorem says to find the antiderivative first. Now what's the antiderivative of 1 over x? We have to recall that is one that you just have to have memorized. And if you think about it, what is, can you recall a function that when you take its derivative, you get 1 over x? As long as you can think about that and you have your derivatives memorized, you can really fastly see that the antiderivative is natural log of x. So the antiderivative is natural log of x, and our notation here is we're going to say we're about to apply the fundamental theorem of calculus. Here's our capital F, and the next step is simply to evaluate capital F at the upper limit minus capital F at the lower limit. And so we have natural log of e minus the natural log of 1. Anybody recall what the natural log of e is? That's one of those special cases. That is 1. Anybody recall what the natural log of 1 is? Or the log base anything of 1 is? Well, 0. So that just took a very difficult Riemann sum and transformed it into a very, very easy fundamental theorem of calculus problem. So the area under the curve, 1 over x, from the left limit of integration 1 to the upper limit of integration e, that little space under the curve has an area of 1. Oops, sorry about that. So that is super easy compared to the Riemann sum we would have to do otherwise. Let's look at an example where we have multiple terms. Because when you have multiple terms, there is more arithmetic that you have to be aware of. And if you're not careful with your arithmetic, you will lose negative signs and you'll have some problems. So let's see here. Let's look at the definite integral. Oh, let's see, from 1 to 2. But of x squared minus 3 dx. Okay? Now, x squared minus 3, I don't believe that is going to be non-negative over 1 to 2. Because remember, what is x squared minus 3? What does the graph look like? Well, it's a parabola with the vertex at 0, negative 3. So it's going to be under the x-axis part of the way from 1 to 2, it looks like. So let's see here. So the interpretation here, since 1 over x is non-negative from 1 to e, the interpretation was that's area. But I'm not sure the interpretation is going to be area here because I think that this function actually dips below the x-axis. So the interpretation here is going to be net area. That is, the area above the x-axis minus the area below the x-axis is the net area of this definite integral. But let's just see what the fundamental theorem tells us. The fundamental theorem tells us, first, find the antiderivative. Well, we've already done the antiderivative of x squared just a moment ago. That's x cubed over 3. But what's the antiderivative of negative 3? Well, it's negative 3x. And we say, all right, well, let's evaluate that at 1 and at 2. So don't forget your notation here. Notation is very important. Okay, so we first have to evaluate capital F at 2. So now capital F has 2 terms. So let's make sure to use parentheses. So that is 2 cubed over 3 minus 3 times 2 in parentheses. That's capital F of A. I plugged in a 2 into this expression. Minus, okay, we have to use parentheses here, capital F evaluated at 1. So that's 1 cubed over 3 minus 3 times 1. And now let's see what happens here. 2 cubed over 3, that's 8 over 3. Obviously 3 times 2, so we have minus 6. Now we have, let's see, minus 1/3 minus 3. So you see here now why those parentheses are very important, because if we didn't have those parentheses, we would have this negative sign not being applied appropriately. So we have 8 over 3 minus 6 minus 1 over 3 plus 3. Okay, so we have, let's see, 8 over 3 minus 1 over 3, that's 7 over 3. Then we have minus 6 and plus 3, so minus 3. So we have 7 over 3, let's see, minus 3 over 3. So that would be minus 9 over 3, so that would be minus 2 over 3 total. So notice the net area here is negative. Okay, so the interpretation cannot be traditional area, because traditional area is always a non-negative quantity. So here again, think about this. Just let's visualize what's going on here. We have a graph. X squared minus 3 has a intercept at negative 3 on the y-axis. Now, what are the x-intercepts? Think about the x-intercepts. That's when you set this equal to 0 and solve. If you set this equal to 0 and solve, you get x-intercepts at plus or minus the square root of 3. So the square root of 3 is about 1.7. So if there's 3, then there would be about positive 3. So maybe 1, 2, 3, that's fine. So about 1.7, this parabola is going about like so. Now, what is the interpretation of net area? Now, we're looking from 1 to 2 is where we're concerned with the integral. So notice here, this little bit of area is what we're looking for. But this little bit is smaller above the x-axis. So from 1 to 2, there's x equals 1. And there's x equals 2. Notice the part above the x-axis is smaller than the part below the x-axis. The part below the x-axis counts in a negative fashion. The part above the x-axis counts in a positive fashion. But because the portion below the x-axis is bigger, and so it's going to be a bigger negative number than the portion above the x-axis, therefore our solution is negative. So net area, a definite integral, can be negative, it can be positive, or it can be 0. What would the situation be where the definite integral is 0? That situation would be, say, when you have maybe an even function and you're integrating, or not even even function, just that's a special case. But anytime you have the same amount of area below the x-axis as above the x-axis, you're going to have an indefinite integral equal to 0. And I meant to say odd function earlier. Sorry, I said even function just a moment ago. For instance, I'll just do an example real fast while we're here. Let's do a trig function. Let's do like the definite integral from, that's way too big. Definite integral from, let's see. Let's do pi, or negative pi to pi of sine x dx. Okay? Now, does anybody recall what the antiderivative of sine x is? Sine x, I think it's negative cosine x. Now, why would it be negative cosine x? Because if you take the derivative of negative cosine, you get negative sine, which you get positive sine. Okay, that trips a lot of students up because, you know, when you take derivatives, you take the derivative of cosine, you get negative sine. But when you take the antiderivative of sine, you get negative cosine. So, like, where the negative sign goes between those two functions when you anti-differentiate versus where you differentiate kind of swaps. So be conscious of that fact. Don't get mixed up there. All right, now we have the antiderivative capital F, and we are indicating here that we're going to evaluate capital F at pi, and then capital F at negative pi, and then we're going to find the difference. And let's see what we get here. So we have negative cosine of pi, and remember it's always minus capital F of A, so minus negative cosine of negative pi. Okay, so what's cosine of pi? Well, cosine of pi is what? Negative 1. Okay, so negative 1. Okay, let's just go ahead and change that to a plus since it's a double negative. Now, what's cosine of negative pi? Well, negative pi and pi are coterminal, so they're going to have the same value. It's going to be negative 1. So we have negative 1. That's a positive 1. Minus 1, 0. So it's perfectly acceptable for a definite integral to have 0 as an answer. Now, why does that make sense? That makes sense because if you consider the graph of sine x, it's an odd function. Okay, so if we look at, say, okay, sine, we're going to pi. Okay, so sine of pi is what? Well, sine of pi is 0. So it's like this. There's positive pi. And there's negative pi. Okay, well, the definite integral is looking at the area between the curve and the x-axis. So this area, and I didn't draw this perfectly, but that purple shaded area and that purple shaded area should be equal if I could draw nicely. Now, since they are equal and one of those regions lies above the x-axis and the other lies below the x-axis, they cancel each other out. So the net area is 0. Okay? The net area is 0. Now, I just thought about something. You know, I've been doing calculus for a long time. I just thought about something, and I realized that you might be slightly confused when I take these antiderivatives, because previously we have always said that when you take an antiderivative, you have to add a plus c. And so I keep taking these antiderivatives, and I have not added a plus c anywhere. But I want to show you why we can skip that step with definite integrals. Okay, with definite integrals, we can skip the plus c. Now, if you're taking an indefinite integral, now how do we know we're dealing with an indefinite integral? An indefinite integral does not have limits of integration. So notice here on all these examples, we had limits of integration. This indicates to us that we are dealing with a definite integral. That is, we're talking about essentially net area. Now, if you have an integral sign, the same exact symbol, except you do not have limits of integration, no numbers on that integration sign, then you're dealing with an indefinite integral, which in that case means you're just looking for the family of functions, like we were in section 5, chapter 5, section 1. For instance, let me just note here. If you simply have, I don't want to waste all my room here, but let's say you just have the integral sign like that versus let's not use, let's A and B. Okay, this is the definite integral. Okay, definite integral. Whereas no limits of integration, indicate that is an indefinite integral. Remember, what's indefinite? That's also known as an antiderivative. Antiderivative. This is a definite integral. So here, what is an antiderivative? What's an indefinite integral? It's a family of functions. So the answer here is a family of functions. Whereas the answer here is going to be, in almost all cases, a number. Now, we are going to look at the second fundamental theorem of calculus, which will, well, not necessarily the second fundamental theorem of calculus, but we will look at situations where a definite integral can result in what's called an accumulation function. But almost always, except for that case where you get an accumulation function, the definite integral is going to result in a number. Maybe negative, maybe positive, but a number. An antiderivative, also known as an indefinite integral, is always going to result in a family of functions. That's why you always have to use a plus c. Always have to use plus c over here. But you don't have to worry about a plus c over here. Now, I will show you why that's true. Let's scroll down and let's look at an example. Let's say, well, let's get some more room here. Let's say we want to look at the antiderivative. Oh, that's a nice one. Let's say antiderivative from 1 to 4 of 3 square roots of x dx. Okay, so the first step is to find the antiderivative. Now, what have we talked about in previous sections? We've talked about how you can factor a constant in and out of your definite or indefinite integral. So that first step is we want to get this square root of x by itself, so we can rewrite this as 3 times the definite integral from 1 to 4. Now the square root of x, let's rewrite that as x to the 1/2 power dx. And now we can use the power rule for integration. So what does the power rule say? It says that we can increase the exponent by 1 and then divide by that new exponent. So let's not forget about our 3 though. So the antiderivative is x to the 1/2 plus 1. 1/2 plus 1 is 3/2. And then we divide by that new exponent, which is 3/2. And now let's go and say, all right, let's add that plus c and see if it makes a difference in our final solution or not. So plus c, and then we are going to take care of our the fundamental theorem of calculus, and we are going from 1 to 4. Okay, let's clean this up a little bit. That is 3 times what? Well, it's x to the 3/2 power. If we flip, we're dividing by a fraction. So we flip the fraction and multiply. We have 3 times 2/3. So I think the 3's are going to cancel out, giving us just 2 raised to the 3/2 power. Not 2. Where'd that 2 come from? 2 times x raised to the 3/2 power. Since we flipped the 2/3, the 3's cancel out, divide out, leaving us with 2 times x to the 3/2 power. And if you were going to strictly apply the distributive property, you would say 3c. But again, we always just say plus c. So now we're going to apply the fundamental theorem of calculus. And what happens? Well, the fundamental theorem of calculus says evaluate capital F at 4. So plug in a 4 here. Let's use parentheses because there's 2 terms. 2 times 4 raised to the 3/2 power plus c. Now c is a constant. We're not substituting for c, only for x. Minus, okay, capital F evaluated at 1. So 2 times 1 to the 3/2 power plus c. Now what happens here? Let's see. What is 4 raised to the 3/2 power? Well, that's 4 cubed, then take the square root. So 4 cubed is 4 times 4 times 4, 64. Square root of 64 is 8. So 8 times 2, that's 16 plus c here. Minus, okay, that's 2 times 1 to the 3/2 power. That's so the third power of 1, then take the square root, is just 1. So 1 times 2 is 2. So we have 2 plus c equals 16 plus c, distributing our negative sign, minus 2 minus c. So what happens? We have 16 minus 2, which is 14, but we have c minus c. So there's no c's left over. And I think I know that will always happen with your c's. That's why I didn't even add the plus c before when we were applying the fundamental theorem of calculus. Now, you don't have to add the plus c when you're applying the fundamental theorem of calculus to a definite integral. However, if you're doing a chapter 5 section 1 problem, it is necessary to put a plus c there. If you're just trying to find the antiderivative, then you do need a plus c. It just so happens that if you're going to apply the fundamental theorem of calculus, that the c's we know are going to add to 0 once we subtract capital F of A from capital F of B, so we don't have to worry about adding the constant of integration. Okay, so that'll just save us just a few seconds every time we do a fundamental theorem of calculus type problem. Okay, so don't worry about your c's, save just a second of time. Other than that, find your antiderivatives just like we did in chapter 5, section 1. So in order to do this section, chapter 5, section 4, you have to know your antiderivatives, because the fundamental theorem of calculus here depends on you knowing your antiderivatives. So we're going to do a lot of trig antiderivatives, a lot of like power rules, and square roots, cube roots, that kind of stuff. So just really make sure to get good practice in on your antiderivatives, because that is obviously the main focus of Chapter 5, and of course, you won't be able to do the Fundamental Theorem of Calculus if you are not extremely familiar with your antiderivatives. In fact, let's just go ahead and look at a trig one before we move on to a new topic here. Let's see here. There's enough room right there to take care of a trig antiderivative. Let's look at the definite integral from 0 to pi over 4 of secant squared x dx. Okay? Now, again, this is where you have to have your antiderivative list memorized, because what is the antiderivative of secant squared? Well, if you have your derivative list memorized, you think to yourself, what do I know I can take the derivative of and get secant squared? Well, if you have that list memorized, you know the answer immediately is tangent. So that's tangent is the antiderivative. Now, it would be plus c, but you know we don't have to worry about that plus c. But we are going to evaluate at pi over 4 and at 0 to apply the fundamental theorem of calculus. And so this is capital F at pi over 4. That's tangent of pi over 4 minus tangent of 0. Okay. So tangent of pi over 4 is what? Well, tangent of pi over 4 is just 1. Recall your unit circle. Pi over 4 has coordinates on the unit circle, root 2 over 2, comma root 2 over 2. So you get 1, tangent of 0, think about 0 radians, sine over cosine, 0 over 1, you get minus 0 equals 1. So the area, now secant squared, secant is definitely non-negative. Secant squared, yeah. So we can think about area under the curve here. Area under the curve from 0 to pi over 4 is going to be 1. Okay? All right, so I hope you get the gist here. Now, we do need to move into some new topics, but I hope you get the gist of what is going on with the fundamental theorem of calculus. You have to first define your antiderivative, capital F. Then, once you find your antiderivative, capital F, you have to look at capital F of B minus capital F of A. All right, so what other theorems did we have? Well, we have this thing called the mean value theorem. Now, you should recognize mean value theorem. We had a mean value theorem for derivatives. So we had a mean value theorem for derivatives. We're also going to have a mean value theorem for definite integrals. Now notice here, these are both very, very close related. What is the mean value theorem for integrals say? It says if f is continuous on the closed interval a to b, there exists a number in C in the closed intervals a to b such that, well, what does that say? It says that the definite integral, so this means net area, or if the function is non-negative, area under the curve, equals f of c times b minus a. What's b minus a? Well, think about it. B is your upper limit of integration, and a is your lower limit of integration. So this is the width of the interval. So b minus a is the width of the interval. So you have the total area equals the width of the interval times something. What that something is the average value. Okay? The average value. F of c ends up being the average value. Now, when I say average value, I mean average y value. Average y value of f of x over a comma b. So it's the average height. When you think y value, think height. Okay? So think height. So the average height of your function over this given interval. So how do you find f of c? Well, that's easy. Divide both sides by b minus a. Remember, a definite integral, that's just a number. F of c, that's just a number. B minus a, that's just a number. So we can clearly divide both sides of this equation by b minus a, and that will give us f of c. So if you want that average height, that average y value, this is all you have to do. Take your definite integral and divide by b minus a, which is the same thing as multiplying by 1 over b minus a. This is what the mean value theorem for integrals does for us. It allows us to find the average height of a function, but more importantly, it allows us to find geometrically, which I think is really cool, it allows us to find a rectangle such that the rectangle, the area of the rectangle equals the area of the, or excuse me, I should say, if this is non-negative, the area over here of the definite integral equals the area of a rectangle. So I think that's pretty cool. You can find a rectangle that has the exact same area as a curved space. So you have an irregular space, and you can find a nice shape via calculus, that is a rectangle, that has the exact same area as that irregular shape. That's what's pretty cool about the mean value theorem for integrals. And it does some other stuff for us too, but that's kind of the geometric interpretation. Let's look at a couple examples. So let's see here. Let's look at, first of all, let's find the average value. So find the average value of f of x on, let's see, 1 to 4, when f of x equals 3x squared minus 2x. Okay? So the mean value theorem tells us the average value will be 1 over, so we'll call it f of c. F of c is the average value, is going to be 1 over b minus a times the definite integral from 1 to 4 of f of x dx, so 3x squared minus 2x dx. That looks like it might be a 9, so let's just fix that. That is definitely a 4. Okay, so this isn't too bad. We have to apply a fundamental theorem of calculus. What's b minus a? Well, remember, that is b, and that's a for sure, just like here on the definite integral. So what's 1 over b minus a? Well, it's 4 minus 1. So it's going to end up being 3. We're going to get the answer here and then divide by 3 is all we're going to do. So let's see here. We have 1/3. Now what's the antiderivative? The antiderivative of 3x squared. Well, if you increase the power of x by 1, then divide by that new power. So you x the cube, x to the third power over 3. 3's cancel out, and you get x cubed. That should be an easy one, right? Because we know the derivative of x cubed is 3x squared. Now, what about the antiderivative of 2x? Again, this should be a pretty easy one because the antiderivative, if you increase the power by 1, it's currently a first power, increase it to 2, divide by 2, you simply get x squared. Which, of course, we know the derivative of x squared is 2x. Okay? So now we're going to apply the fundamental theorem of calculus from 1 to 4. So we have a 1/3 hanging out front. Now, what's the fundamental theorem say? Let me use a bracket since I have a 1/3 out front, and then I'll use parentheses inside. So you have 4 cubed minus 4 squared minus, okay, this is capital F of A right here. That is capital F evaluated at 4 minus capital F evaluated at 1. So 1 cubed minus 1 squared. So we have 1/3. And then what's left over? Okay, 1 minus 1, that's 0. So we have minus 0, that's easy. 4 cubed, that is 64. Minus 4 squared is 16. So 1/3 times 48 equals 16. So 16 is the average value. Average value of f of x on 1 to 4. Now here's the cool geometric interpretation of this mean value theorem. Now I'll draw a quick sketch. Then we'll look on Desmos as well to get a nice graph. So we graph f of x, 3x squared minus 2x. It looks something like this. Okay, that point right there, again, this is not perfect, but that's 1, 1. This point over here is 4, 40. Okay, now we were looking at the definite integral from 1 to 4. So the definite integral, since this is non-negative, the definite integral is all of this shaded area. Okay. Now, what does the mean value theorem do? The mean value theorem for integrals says, all right, you can find the average value. The average value is 16. So, okay, that's 40, that's 1. So 16 is going to be right here in the middle somewhere. Let's just say it's about right there. Oh, I think it's probably a little bit lower. So 16 is right there. That's the average y value. But what it also does is it gives the height of a rectangle such that if we superimpose a rectangle over the exact same interval, the shaded area of this rectangle will be equal to the shaded area under the curve. Now, it looks like I didn't draw that very nicely. It looks like the area of that rectangle is probably bigger than it should be, but it's pretty close. So, what we can see here, and why does that work? What's the area of this rectangle? Well, it's width times height. What's the width here? So width is 4 minus 1 is 3. 3 times 16 equals 48, and that's area of rectangle. What's the area of the definite integral? Well, what was the definite integral? The definite integral was 48 before we divided by 3 and got 16. Notice, so this entire thing, everything here is the definite integral, that is area under the curve, until we divided by 3 to get 16. So the definite integral from 1 to 4 of f of x dx also equals 48. And that's area under curve. So we found a rectangle, a nice shape that we can readily access. The area of the rectangle we found is equal to the area of this irregular shape under the function f of x. So that's why the mean value theorem is really cool. because we are able to find a nice rectangle that has the exact same area as the definite integral. And this works even if the interpretation is not area. If the interpretation is net area, like if your function goes non-negative, this still works. So anyway, it's a really cool application. A really cool application of definite integrals is the mean value theorem for integrals. And also notice, not to overshadow the fact that 16 is the average y value. That is, 16 is the average height of this blue curve over the interval from 1 to 4. So you get average height, and that's also the height of your rectangle that will give you the same area as the area of the definite integral. So pretty cool stuff if you ask me. All right, so let's look at a very similar example. Let's find the average value of f of x equals, let's look at 9 minus x squared. 9 minus x squared. So f of x is 9 minus x squared. Find the average value of f on the interval from -3 to +3. And let's also determine where f of c occurs. That is, find the x value where f of c occurs. Okay, now we're going to follow the exact same steps we did just a moment ago. We're going to say f of c equals 1 over b minus a. So b is 3, a is -3. So that is 3 minus -3 times the definite integral from -3, that's a, to +3, that's b, of 9 minus x squared dx. Okay, so that's equal to what's 3 minus -3, that's 1 over 6, times the definite integral. Well, let's actually just go ahead and find the antiderivative. The antiderivative is 9x, then minus x cubed divided by 3. And according to the Fundamental Theorem of Calculus, we need to evaluate that at -3 and at +3. Okay, so we have a 1/6 hanging out front. Let's use brackets and then apply the fundamental theorem. So let's see, 9 times 3, that's 27. Oh, let's just substitute. Let me not multiply. 9 times 3 minus 3 cubed over 3. That's the first, that's f of b minus f of a. So that's 9 times -3 now, minus -3 cubed over 3. Okay. Let's see here. Close parenthesis, close bracket. So we have that 1 over 6 out front. And now what do we have? That's 27. Now what's 3 cubed? 3 cubed is 3 times 3 times 3. So 27 over 3. 27 over 3 is 9. Okay, 3, yeah. 27 over 3 is 9. So 27 minus 9 is 18. So that first set of parentheses simplifies to 18 minus, okay, -3 cubed is -27, but we have a negative out front, so it's going to be +27 over 3. So that's 9 again. But then we have 9 times -3, so that's -27. So we have -27 plus -27 plus 9 is negative 18. So negative 18. So you have negative 18 minus the negative 18. We have 1 over 6. 18 plus 18 is 36. So 36 divided by 6, we get 6. So that's f of c. That is the average value of this curve over negative 3 to 3. The average y value, the average height. Okay. Now notice here, or actually, let's look at a picture in Desmos to get a nice picture of what's going on, and then let's also find where this average value occurs. It could occur at one point, or it might occur at more than one point. So if this is the average y value, how might we figure out where that average y value occurs? That's just a purely algebraic question. We set 6 equal to 9 minus x squared and solve for x. These will give us the x values where that average value occurs on f. So let's see here. That's equivalent to saying x squared equals 3. X squared equals 3. If you add x squared to both sides, subtract 6 from both sides. And so that tells me x equals plus or minus the square root of 3 using the square root property. So this average y value occurs at x equal plus or minus the square root of 3. Okay? So some of the homework is going to be phrased like that. Not only do we want to find the average y value, but we also want to find the x values where those average y values occur, or average y value occurs. There's only one average value, but there could be multiple x values where that average value occurs. Because right here, this is a semicircle, if we recall. We commonly look at situations, oh, that's not a semicircle, that's a parabola, sorry. If there was a square root, it would be a parabola. I mean a semicircle, but that's an upside down parabola with the vertex at 0, 9. Now let's look at a picture of this. I'm going to look at a nice graph. Let's look at I'm going to use Desmos again. Let's move over here real fast. Now I created another visualization to show the mean value theorem. Okay. The mean value theorem is also cool. So let's look. We had 9 minus x squared. 9 minus x squared. Okay, let's zoom out here. Now we were looking at negative 3 to positive 3. So let's move the slider here. That's A. And we have B. Now, the average value we said was 6. And what does the graph indicate? The average value is this horizontal line here, which is 6. Now, remember what the geometric interpretation was? The geometric interpretation was that average value gave the height of a rectangle such that you could superimpose a rectangle with a base equal to the width of your integral. And the area of that rectangle is going to have the exact same area as the area under the curve of your original function. So here the original function has that green shaded area, okay, that right there, and then this blue rectangle has the exact same area. But of course a rectangle is super nice because it's a nice shape that we can easily work with, as opposed to that weird shape that it's hard to work with. So that's why that is why the mean value theorem for integrals I think is really cool, because you transform a complicated shape into a simple shape, and they have the exact same area. Okay, area is 36 in both cases. The area of the green portion, 36. Area of the blue portion, 36. The exact same in both cases. I think this is I think it's really cool. If you want to look at I drew a picture of our previous example. Let's look at a nice picture. The first example we did was 3x squared minus 2x. And we were looking at the interval from 1 to 4. So let's change this to 1 and change this to 4. Okay, zoom out a little bit. So the average height we found, as indicated here, is 16. That's the exact same conclusion we reached. And notice, oh, that's a very tall portion here. But the shaded green area here, that is like the definite integral. That's the area you get if you take the definite integral. But what the mean value theorem for integrals says is, hey, we can find a rectangle that has the exact same area where the base is the exact same width as the width of the integral. So the width here was between 1 and 4. So the width was 3. So here's the rectangle that has a width 3 and has a height that's equal to the average height over the interval, which is 16. And clearly, if the height of that rectangle is 16, the width is 3. 16 times 3 is 48, which is the exact same thing as the area under the curve, the definite integral from A to B. Again, I think this is a super cool application. And if you want to figure out, again, we didn't solve this here, but you can figure out what x value leads to that average value by simply setting f of x, which in this case is 3x squared minus 2x, equal to 16, and solving. Okay, so the average height was 16. Solving that quadratic equation, solving the quadratic equation, 3x squared minus 2x equals 16. Maybe that, I'm not sure if that's going to have a nice answer. You might have to use the quadratic formula or completing the square if it doesn't factor. But anyway, mean value theorem for integrals, really cool stuff. So sometimes just be careful with directions. You might be looking for the values of c. Like here I said occurs when x equals plus or minus 3. Sometimes the homework will say find the value of c. Now remember, a c value is always a x value. C is just a specific x value. So if you see directions on a homework, quiz, or a test say find the value of c where the average height occurs, you're just simply looking for the value of x. X values where that average value occurs. Again, if we would go up here, just to visualize the picture, that if the average height is right there, this is the c value we're looking for. That's c is what we're calling where the average height occurs. So the average height occurs right there. Where does that occur on the original function? All you have to do is, like I said, is set f of x equal to the average height and solve, in this case, using quadratic equations or factoring and using the zero product property. Okay? Let's see, what else do we have? We have the second fundamental theorem of calculus, and we need to talk about accumulation functions. So we're getting close to the end here, but we do have a few more things to talk about. The accumulation function is what happens if we take the definite integral. So let's see. Let's take the definite integral. Now, let's look at 0 to x. So we haven't seen this example yet. What happens when you don't have a number there? When it's a variable. And we look at cosine of t dt. Now the reason I use t's all of a sudden is because I don't want the variable of integration to get mixed up with this variable x here. They're two different variables, but the t's I could just have easily used any other variable I wanted to. I just don't need to use x's here so we don't get confused. Okay? Now, what this is going to do is give us an accumulation function. What an accumulation function does is it gives us a capital F such that when we we evaluate this integral, the result is going to be a function, and that function is going to allow us to find area under cosine t, and allow us to plug in, essentially it's the function is going to embed the lower endpoint of 0, and then all we have to do, if we want to find the definite integral from 0 to pi over 2, plug in pi over 2 into capital F. If we want to find the definite integral from 0 to pi, simply plug in pi. Now, let's show you how that works. It's called an accumulation function. So proceed as usual. Let's just apply the fundamental theorem of calculus just like we have been doing, and don't let that x there bother us. So what does the fundamental theorem say? It says to take the antiderivative. So what's the antiderivative of cosine? It's sine. How do we know it's sine? Well, if you take the derivative of sine, you get cosine. That's why we know it works. Now the fundamental theorem says we're going to evaluate this at 0 and x, which certainly equals, let's see, we evaluate capital F of the a, which in this case is x, so sine x minus sine 0. Capital F evaluated at 0, which equals sine x. Okay, now why is that really cool? This is cool because this essentially has, all I have is sine x equals capital F of x. But what this allows me to do is I can just say evaluate capital F of, or actually I'll write out the intervals. If we want the definite integral from 0, say to pi over 6 of cosine of t dt, all we have to do is evaluate capital F of pi over 6. Because capital F already has the lower limit of integration essentially embedded into it. I let the upper endpoint be variable. I let the lower endpoint be 0. And so when I evaluated this definite integral, I was left with just an accumulation function, which all I have to do here is say sine of pi over 6, and sine of pi over 6 is what? Well, it's 1/2. If I want to evaluate the definite integral from 0, let's say, to pi over 4, okay, I could just go ahead and completely evaluate another definite integral, but I already have my accumulation function. My accumulation function is just sine of x, which we get, of course, root 2 over 2. What if I wanted to then look at the definite integral from 0 to pi over 3 of cosine t dt? Well, I know that's capital F of pi over 3. So that is equal to sine of pi over 3, which is equal to root 3 over 2. If I want to look at the definite integral of cosine of t dt, say of 0 to pi over 2. Well, 0 to pi over 2, that's like saying capital F of pi over 2. So that's sine of pi over 2. So what's sine of pi over 2? Well, that's 1. So what's happening here is, think about a picture. We have, let's just draw cosine. Okay, let's see. Cosine, we went to pi over 2. So cosine looks like this. At pi over 2, it's 0. and pi, so pi over 2 and pi. Okay, so cosine starts up here at 1, goes down like that, like so. Okay, at pi over 2, it's 0. Okay, so what we're doing here is we looked at pi over 6. We looked at pi over 6, so there's pi over 2. We looked at pi over 6, pi over 4, so pi over 4 is right in the middle. Then, of course, pi over 6 is to the left and pi over 3 is to the right. So the first time we looked at the integral from 0 to pi over 6, that was like this little bit of area right here. But then we looked at the definite integral from 0 to pi over 4, which was all of this added to it. So we added some to it. Then we looked at the integral from 0 to pi over 3, which was like somewhere over here, and we keep adding to it. This is why this is called an accumulation function, because the lower endpoint of 0 is built into this accumulation function. And now all we have to do is evaluate capital F evaluated at our upper endpoint, because the lower endpoint is already built in. These are called accumulation functions. So we don't have to have a constant on both of the limits of integration. In fact, you don't have to have a constant on either of them. Now, most of the time we will, but you don't have to have a constant limit of integration for the upper or lower limit. Let's look at another example. Let's just look at a simple example. Let's look at the definite integral from 0. Oh yeah, let's do 0. Now let's do 1. 1 to x of t squared dt. Okay, so if we just proceed as normal, we first, according to the Fundamental Theorem of Calculus, find the antiderivative. The antiderivative is t cubed over 3. And we evaluate that at our limits of integration, apply the fundamental theorem, and we get x cubed over 3 minus 1 cubed over 3, which is 1/3. That is our capital F of x. Now, if we want to find the integral from 1 to any point x, all we have to do is evaluate capital F of x. So this way, I don't have to evaluate if I want to find the definite integral of t squared from 1 to 5 and then from 1 to 3. I don't have to do two separate definite integrals. I can just evaluate capital F of x twice. So if I want to look at the definite integral from 1 to 5, all I have to do, so of t squared dt, all I have to do is evaluate capital F of 5, which is 125 over 3 minus 1 over 3 equals 124 over 3. Does that reduce at all? Maybe. Nope, doesn't reduce. Okay, but then let's say right away I wanted the definite integral from 1 to 3 of t squared dt. Well, instead of going ahead and finding another antiderivative, doing another fundamental theorem of calculus application, I can just evaluate capital F of 3, which I look at, that's 3 cubed over 3 minus 1 over 3. So 3 cubed over 3, that is 27 over 3 minus 1 over 3, so that's 26 over 3. So this allows me, I would use the accumulation function in those situations where you want to find multiple definite integrals over the same function, and where the left-hand endpoint is the same. Now, what happens if you pick an endpoint that is smaller than 1 in this case? I think we'll be fine. It looks funny. I think it's fine. What if we looked at, say, the definite integral from 1 to 0? From 1 to 0 of t squared dt. Well, what happens? You're evaluating capital F at 0. Well, what's capital F of 0? It's, sorry about that, it's 0 cubed over 3 minus 1/3. So we get negative 1/3, which is to be expected because we always get a weird answer when the upper limit of integration is smaller than the lower limit of integration. Okay, we are integrating backwards essentially, and if the answer from which we can then say actually, by the way, we can then say for sure that 0 to 1 of t squared dt is equal to what? We can say it's equal to positive 1/3, according to some of those rules we talked about in the previous lesson. If you transpose the limits of integration, you just change the sign on your solution. Okay. So again, this accumulation function is a really neat because it allows us to embed into our capital F function. It allows us to embed the lower endpoint, and then we can find the definite integral from that lower endpoint to any other endpoint we want by simply evaluating capital F at the upper endpoint. So anyway, pretty cool, and that's actually going to inform our discussion next about the second fundamental theorem of calculus. So what does the second fundamental theorem say? The second fundamental theorem way up here says that if you do that exact thing we just did, that is, you evaluate f of t dt, and again, t is just a dummy variable here. It can be any other letter you want. We only use a different variable so as not to confuse with x. If you do the exact same situation that we just did, that is, you integrate from some constant lower endpoint a to a variable upper endpoint x, you find the accumulation function, but then you take the derivative of the accumulation function, you get lowercase f of x. So let's verify that. So we already have two accumulation functions. We have the accumulation function f of x equals sine x. So the fundamental theorem of the second fundamental theorem of calculus tells us this: f prime of x at capital F prime should equal cosine. So let's see. Capital F prime of x equals what? Well, d over dx of sine x equals cosine x, which is exactly where we started, and that's what the second fundamental theorem of calculus says, or what it guarantees, rather. Okay? Guarantees that, first of all, if f is continuous, you can find an antiderivative of capital F, and then if you take the derivative of capital F, you get the original integrand, except in terms of x instead of t's, because, again, t is just a dummy variable. So where's capital F? Capital F is right here. The second fundamental theorem of calculus says the derivative of capital F of x should be the original integrand, except evaluated at lowercase x, or at x instead of t. So what is the derivative of capital F right here? Well, the derivative of x cubed is 3x squared. Well, 3x squared over 3 is x squared. The derivative of negative 1/3 is 0. So capital F, the derivative of capital F is x squared, which is the original integrand evaluated at x. So here's kind of like the lazy way to do it. The lazy way, if you want to take the derivative of the derivative with respect to x, of 1 to x of t squared dt. The lazy way to do this is simply to replace the t's with x's and say, easy, answer's x squared. That's what the second fundamental theorem of calculus tells us. That we can, first of all, if f is continuous, we can find an antiderivative. And after we find that antiderivative, we can take its derivative and come back to our starting point. The only thing you have to be careful of is what happens like if you integrate, say, from 1 to x squared, then you have to use the chain rule, but that's not hard, okay? So this is what the second fundamental theorem of calculus tells us, that we can, first of all, find an antiderivative, and then once we find that antiderivative, if we take its derivative, we get our original starting point back in terms of x. That is the second fundamental theorem of calculus. Let me look at one more. It looks more difficult, but it's not really more difficult because this is pretty easy. It's hard to prove this, but once it's proved, it's not so bad at all to apply it, that's for sure. Let us look at, let's see here. Let us look at evaluate the derivative with respect to x of the antiderivative 0 to x of the square root t squared plus 1 dt. Now, here's what the second fundamental theorem of calculus guarantees us. If this function is continuous, now the square root function is continuous from 0 to a positive number. Okay. If that is continuous, which it is, it's a square root function. Actually, this is this is continuous everywhere because that is a t squared. So since we're doing t squared, that's continuous everywhere. Sorry, I missed that at first. Since that's a t squared, that's continuous everywhere. And since this integrand is continuous everywhere, we're guaranteed to be able to find an antiderivative. Now, the second fundamental theorem of calculus does not guarantee that antiderivative is easy to find. It might be nearly impossible for us to find as far as methods in Calc 1 or maybe even Calc 2. So it may be very difficult to find using what's called elementary methods. But if it's continuous, its antiderivative does exist somehow. And then when you take the derivative of that antiderivative, you are going to get x squared plus 1. That's what's neat about the fundamental theorem of calculus part 2, is that if you can find that antiderivative, that's cool, find it. But when you take the derivative, you're going to get the original integrand, except now with x's in it instead of t's. Okay. For instance, let's say, let's see here, another hard one that we don't know how to do at this point. In fact, you probably won't know how to do it until you get to Calc 2. If you look at, say, if you want to find the derivative of the definite integral from 1 to x, let's say of t sine t dt. So you have a variable times the sine of that variable. That's actually going to be a kind of tough problem that you're going to tackle in Calc 2, not in Calc 1. Okay, but the fundamental theorem of calculus says if this function is continuous, which, okay, sine of t is continuous, so the product is continuous. If this function is continuous, which it is, there exists an antiderivative. You can find that once you get to Calc 2. But for the time being, we can say that once you find that antiderivative and you take its derivative, you get x sine x. That is what the second fundamental theorem of calculus tells us. Anyway, pretty cool. Like I said, hopefully I will have time to create a second special video lecture that talks about the second fundamental theorem of calculus. I'll be doing that at some point in the near future, so that I can explain, where does this come from, why does it work. Here's the practical application as far as we're concerned right now. But it is very important, and it kind of has some really cool how it works, how you show that left-hand side equals right-hand side here. Pretty cool stuff. But for our purposes here, what the second fundamental theorem guarantees us is that if you can show that the function's continuous, like here it is continuous. Remember, we have properties of continuity way back in chapter 2. As long as you can show that the function's continuous, then we are guaranteed that it has an antiderivative. And once we take the derivative of the antiderivative, we get the original integrand back in terms of x. Okay? All right, last thing, net change. Net change, and then we will call it a day. All right, it might take a little while to do net change. This is a little bit longer of a lecture than usual, but this is the culmination of the class. This is the next section, which is 5.5. That is just a couple more techniques of how to integrate. Here we're tackling a lot of really important theorems. Now the net change theorem, here's the nice thing. Let's compare it to the first fundamental theorem of calculus. Notice what is different. Okay, we're taking the definite integral from a to b, definite integral from a to b, lowercase f of x dx, uppercase f of x dx equals uppercase f of b, uppercase f of b, uppercase f of a, uppercase f of a. Notice the only thing different is that we have a capital F prime here instead of an f of x. But what do we call capital F prime of x? We call capital F prime of x lowercase f of x. Now what this is trying to communicate here, it's just a notational difference. This is just a restatement of the first fundamental theorem of calculus. What the restatement is trying to show is that we are taking the derivative, we're taking the integral, the definite integral of a derivative, which is a rate of change. So capital F, again, we already knew that conceptually, that when we were taking the antiderivative of a derivative, but this is just trying to stress the fact we're taking the antiderivative of a derivative. A derivative is a rate of change, and the first fundamental theorem of calculus is going to yield the net change. Kind of like if we were talking about area, it yielded net area. Because your function, we're not guaranteed that the function is going to be non-negative necessarily. And so if the function is non-negative, then the geometric interpretation is plain old area. If the function is not non-negative, then the geometric interpretation is net area, much like this picture right here. So net change theorem, again, it's just a restatement of the fundamental theorem of calculus part 1, and it just stresses that you're integrating over a rate of change. So you're integrating over something that's changing, and so you're accumulating change is what you're doing. You're accumulating stuff. All right, so let's just see how that works. Again, this is going to be for all practical purposes, we're going to work these in a very similar way to what we have been doing just now. So let's look at a first example. It says a chemical flows into a storage tank. A chemical flows into a tank at a rate of 180 plus 3t, 180 plus 3t liters per minute. All right? Okay, where t is measured in minutes per minute, and t equals minutes. Okay? And so the question is, find out how much liquid or chemical flowed into the tank during the first 20 minutes. So how much chemical flowed into the tank over the first 20 minutes. So this is like an application, but what are we told here? We're told that here's the rate of change, and we're trying to figure out how much of chemical has accumulated in this tank over the first 20 minutes. So this indicates to me 0 to 20, first 20 minutes. And so we are looking at the definite integral from 0 to 20 of 180 plus 3t dt. And so again, at this point, it looks exactly like the Fundamental Theorem of Calculus Part 1. The only thing we're stressing here is that this is a rate of change. This is a derivative. So we take the capital, we find capital F, so that's what, 180t plus 3t squared over 2, and we're going to evaluate that at 0 and at 20. Now let's see, what does that equal? It's 180 times 20, so we have 3,600 plus 3 times 20 squared, so that's what, 400 times 3 divided by 2, you get 600. So that's capital F evaluated at 20 minus capital F evaluated at 0. Well, you have a 180 times 0 plus 0 squared times 3 over 2. Anyway, that's 0. So you have what? 3,600 plus 600, you get 4,200. Again, that's liters. So that's just a straightforward application of the net change theorem. All we're doing is stressing there that we are evaluating a definite integral where the integrand is a derivative, is a rate of change. Now, last thing I want to look at is what happens when you take the integral of a velocity, a definite integral of a velocity function, because this is another application of the net change theorem. Okay, the definite integral. What happens if you take the definite integral? So let's just look at an example here. Well, let's just keep it general. A to b of v of t dt. Remember, velocity as a function of time, velocity of t dt, the integral from a to b, the interpretation of this. So if you take the definite integral from a to b of a velocity function, the interpretation is going to be displacement. Remember, displacement, that's how far away you are from the starting place, from your starting point. Displacement. So how far away is an object at time B as opposed to time A? Okay? So distance between A and B. Okay? Displacement is going to be the distance. Actually, I shouldn't say between A and B, sorry. The distance between an object at time A and time B. So displacement, again, for you guys that are in physics class, I'm sure that is going to be plenty familiar to you. Now, that's opposed to the integral from A to B of the absolute value of V of t dt. That's going to give us total distance traveled. So if you take the definite integral from A to B, I should say over time AB. So over time AB in both cases. So if you take the absolute value of your velocity function and integrate over AB, the answer is going to be the total distance traveled of that object over time AB. If you take just the regular integral, standard integral from A to B of your velocity function, then the result is displacement. That is, how far away is the object at time B from where it was at time A. So displacement versus total distance. Make sure to really differentiate those two concepts in your mind. Displacement's how far away the object at time A is from time B, but total distance traveled is the amount of time, length of the particle or the object traveling. Clearly, they could be equal at some points. At some times, they could be equal. Like, for instance, if you travel in a straight line, then displacement equals total distance traveled. So let's say here's a position at time A, and here's a position at time B. If you travel in a straight line, as straight as I can draw it, displacement equals total distance traveled. But let's say I travel in a squiggly line. Well, that's total distance traveled, and displacement is still the distance between those two objects. Okay? The distance between A and B is still that straight line distance, but distance traveled is the blue line. So clearly in this case, displacement is a much smaller quantity than total distance traveled. But if you travel in a straight line, then displacement does equal total distance traveled. Now, what's kind of the interpretation here? I suppose you can think about the geometric interpretation. If your velocity function is non-negative, so let's say here's your velocity function. If your velocity function is non-negative, then displacement is going to equal total distance traveled. Okay, that is, when you integrate your velocity function, when you integrate from A, let's say there is B, from A to B, the definite integral of the absolute value is going to be the exact same thing as the integral of the original function. Okay, but let's say your function is not non-negative. Let's say your function goes like this. So there's B and there's A. If you integrate your velocity function, you have some of it's negative down here, most of it's positive, but to get the definite integral, you have to add this, subtract this, and so the interpretation is that displacement does not equal total distance traveled because your velocity function was not non-negative. Now, this begs the question of how do we deal with absolute value? And so we'll have to tackle that question in just a minute. So let's look at, first of all, just a pretty standard example here. Let's look at a velocity function that is not too terribly difficult to deal with. Let's look at when a velocity function v of t equals t squared. Oh, actually, let's even easier first. Let's start with a linear function. Let's say 2x minus 2. Let's say that's our velocity function. Okay. Now let's look at the interval from let's say 1 to 5. Okay, 1 to 5. Now, if you think about this, that's a linear function. Its not non-negative. Okay, let's think about what the graph looks like. Just a little sketch over here. That has a slope of 2 and a y-intercept of -2. Now, where is the x-intercept? The x-intercept, if you set this equal to 0 and solve, would be at 1. So here is a rough sketch of what this velocity function looks like, v of t. Oh, you know what? I made a boneheaded mistake. I need a t there. V of t. Sorry about that. So you have v of t equals 2t minus 2 over 1 to 5. Okay? So let's see here. If we want to find displacement over time 1 to 5, we simply take the derivative, the definite integral from 1 to 5 of 2t minus 2 dt. What do we get? Well, we have, let's see, the antiderivative would be t squared over 2, so 2t squared over 2, so t squared minus 2t. Now we're evaluating at 1 and 5, so let's see here. That would be 25 minus 10 minus 1 minus 2. Okay, that's just the fundamental theorem of calculus. Capital F evaluated at 5, 25 minus 10. Capital F evaluated at 1, 1 squared minus 2. So what do we have here? We have 25 minus 10, that's 15. 15 minus 1 is 14. But then minus -2, so 14 plus 2, we get 16. So that would be displacement. Okay? Displacement. Now, if you think about the picture here, let me shade what we did geometrically. We went from 1 to 5, so we have, let's see here, there is 1. Oh, you know what? Ah, I messed up here. I meant to include some negative parts. Let me change this a little bit. Sorry about that. Let me change this endpoint. I wasn't even thinking. I was on autopilot here. Let's change that 1, that 1. All it does is change this right here. Let's go from 0. Let's go from 0 to 5. So 0 goes there, 0 goes there, 0 goes there. All it changes is, okay, now we have a 0, calls capital F is 0 squared minus 0. So now that just changes this answer right here. And we have what? 25 minus 10 is 15. Now, geometrically, what was going on there? We're looking at the integral from 0 to 5. Let's just say 5 is right there. Now, what's f of 5? F of 5 is 10 minus 2 is 8. So we have this triangle, 0 to 5, remember. So we have this triangle is part of our solution. But remember, if you have parts of your definite integral where the area is below the x-axis, this counts in a negative fashion. So we have this little bit of area in a negative way, this triangle of area in a positive way, so net area equals 15. You can verify this using simple geometry like we did in the previous lesson. Let's see, we said that was the point 1. So 1 minus 5, this big triangle has a width of 4 and a height of 8. So 4 times 8 is 32. 32 divided by 2 is 16. So the height there is 16. The area is 16 of this green shaded triangle, the part above the x-axis. The part below the x-axis, the width of that triangle is 1. The height is 2. 1 times 2 divided by 2 is 1. So the area of this red rectangle is 1, or this orangish red rectangle is 1. So 16 minus 1, net area is 15. Now, how does the absolute value change those calculations? If you look at the absolute value, that is, okay, this is displacement. So what we calculated was displacement. That is, if this particle or an object is traveling with this velocity from time 0 to 5, it is 15 units away from where it started. That's displacement, 15 units away. But now, what about, let's do total distance traveled. If we look at total distance traveled, we need to look at the definite integral, again, from 0 to 5, but now of the absolute value of our velocity, which is the absolute value of 2t minus 2 dt. Now, we haven't talked about how to evaluate absolute value integrands yet. With absolute value integrands, what we have to realize is what absolute value does to a graph. Absolute value for a graph takes anything that was below the x-axis and reflects it above the x-axis. So we talked about this in a prior lecture. If you haven't seen it, check it out. The previous section. What absolute value does is changes the graph so that anything below the x-axis, this whole portion of the line down here, it reflects it and makes it go like that. So now, instead of having anything below the x-axis, we have this little bit of area that is now positive. So that teal portion is the exact same area as that kind of burnt sienna kind of color. They're the same area, but now it's teal and it's above the x-axis, so it's counted in a positive way. So the absolute value makes the graph completely non-negative. So now what we have to do there algebraically is break this integral apart into where it changes, where where the x-intercept in the original function was. Okay? Now where do we find that x-intercept? We found that point was x equal 1 because we set this equal to 0 and solved. So the absolute value only affects portions of the function that are below the x-axis. So we have to figure out where does this function change from being below the x-axis to above the x-axis. Because the portions that were already above the x-axis, absolute value does nothing to change that. But the portions that were below the x-axis, the absolute value reflects it above the x-axis, and so we have to consider that with our definite integral. So we have to break this definite integral into two pieces. From 0 to 1 of absolute value of 2t minus 2 plus the definite integral from 1 to, what was the endpoint? 5, absolute value of 2t minus 2 dt. Now that was a property we discussed in a previous lecture. Now, so this is the little space of that burnt sienna color. And absolute value does what? Absolute value makes it positive. Now here's one way to think about it. You could algebraically use the definition of absolute value to say, okay, absolute value says if this was already negative, make it positive, which means take the opposite of it. So we could remove the absolute value signs and say this. Integral from 0 to 1 is negative 2t minus 2 dt. That's what the absolute value tells us to do. If your item is negative, take the opposite of it. We know that over the interval from 0 to 1, this function is negative, so take the opposite, which means we flip it above the x-axis. Now, 1 to 5, we already know this is positive, so we can just remove the absolute value signs. Because if you take, say, the absolute value of 3, it is 3 because it was already positive. This function is already positive over 1 to 5. So we don't have to worry about the absolute value here because it was already positive. Okay? Now, what can we do here? The thing to notice is that what's happening. We can factor out that negative sign and simply put a negative sign out front, and now we have the same integrand in both cases. We have the same antiderivative in both cases, but we have to do two separate applications of the fundamental theorem of calculus. So let me actually move this equal sign over to the left because we're going to need more room. So we're going to have negative. All right, what's the antiderivative? Antiderivative of 2t minus 2. Well, we already have found that. We have up here t squared minus 2t. So that is t squared minus 2t. Now we need to evaluate that from 0 to 1 and add that to the, again, exact same antiderivative, except now from 1 to 5. So we're going to have two applications now of the fundamental theorem of calculus. There is a negative sign in front of this one. So what do we have here? We have a negative, okay, t squared at 1, that is 1 minus 2, minus, okay, 0 minus, let's just call that 0, right? 0 squared minus 2 times 0 is 0. So we can just back up and say, there's the first application of the fundamental theorem of calculus. That 0 made things a lot easier. But then we're also going to have, all right, this evaluated at 5, so 25 minus 10, minus this evaluated at 1, which is 1 squared minus 2. Almost running out of room here. Okay, almost have it. 1 minus 2 is negative 1. Negative 1 is positive 1. Plus, okay, we have 25 minus 10, that's 15. 15 minus 1, that's 14. Okay, 14, then minus negative 1, or excuse me, let me back up. 15 minus 1 is 14, but then we have negative 2, so that's plus 2, 16. So we have displacement, excuse me, total distance traveled is 17 as opposed to displacement is 15. Now, why does that make sense geometrically? Why does that 17 make sense? Now, what do we figure out the area here was? The area of this green shaded triangle we found was 16. The width was 4. The height was 8. 4 times 8 is 32. 32 divided by 16. So by geometric area of a triangle, the area of that big triangle is 16. Now, we've previously, when we didn't take the absolute value, we found the area of this little red burnt sienna triangle was 1. But since it was below the x-axis, it counts as a negative 1. But when we take the absolute value, we flip that little triangle onto the above the x-axis. And so all of a sudden it doesn't have an area, it still has an area of 1, but it's not counted in a negative fashion. So it's counted in a positive fashion. So we have 16 plus 1, and we get 17, as opposed to subtracting 1 from 16 to get 15. So notice here, displacement was not equal to total distance traveled because the function was not non-negative over the interval of interest. So if the function is non-negative over the interval of interest, then total distance traveled will equal displacement. But if your function is negative anywhere over the interval, then you have to take into account that total distance traveled is not going to be the exact same number as displacement. In that case, total distance traveled is going to be a bigger number than displacement. Okay? It's possible for them to be equal if the function is non-negative. Now, I think what I'll do is, I was going to do a quadratic, but I think I'll stop with that because I'm kind of running out of room here. So I wanted to look at a couple more examples, and I posted, these are just kind of homework problems that I wanted to kind of talk about. They were interesting homework problems. And the first one is this. It says we're given the function g of x. Now this is an accumulation function, notice. It's the accumulation of f of t from 0 to x, okay? So we're not given any specific function of f of t, but we're told here's the graph of f. So here's f of t as the graph. Now we have to remember this is an accumulation function. Okay, it's an accumulation function. And in the previous slide, we called that capital F. They're calling it G here, so don't worry about the notation difference. Okay, but what you notice is it's accumulating area. The lowest endpoint is 0, and we're going to let the upper limit of integration vary. So essentially what this is asking us is G of 0 is the integral from 0 to 0 of f of t dt. Well, what do we know for sure that has to be? That's a 0 because where the upper and lower endpoints are the same. What about G of 2? And again, that's looking at the definite integral from 0 to 2 of f of t dt. Now, we don't have a function to formally integrate, but let's look and see what we estimate the area to be. So this would be the area under the curve from 0 to 2. Let's see, there's 1 unit, 2, 3, 4, 5, 6, I don't know, maybe 6 3/4. Maybe 6.75. I'll say approximately, because again, we're just estimating here. Again, all I'm doing here is finding the area under the curve between the vertical line x equals 0, the vertical line x equals 2, and the horizontal line of the t-axis at this point. So 1, 2, 3, 4 squares, 5 squares, 6 squares, and maybe 3/4 of a square. Now what about G of 4? I should label these. That's a G of 0. This is G of 2. G of 3. Let's see here. Nope, we're not doing 3, we're doing 4. G of 4, that's the definite integral from 0 to 4 of f of t dt. Now, let's see. So now that's everything. It looks like the function t has an x-intercept at 4, so it's all of this area here. It's almost like triangular shapes. Let's see, 1, 2, 3, 4, 5, 6, 7. Looks like 7 whole squares. 1, 2, 3, 4, 5, 6, 7. Maybe 7.5, and then we said 3/4, so 7.5, 8.25 maybe, approximately. Again, we are simply estimating here. What about G of 6? G of 6 is the integral from 0 to 6 of f of t dt. Now notice here, the function's not non-negative anymore. So what's the difference? Okay, we went from 0 to 4, we found we estimated 8.25. Now if we're going from 0 to 6 now, that's let's see, how much is negative? I would say maybe 1.25, or maybe 1. That looks about what, 1 unit. There's about 3/4 and 1/4 of a square. So I would say maybe that's about like an area of -1 that we need to add to this 8.25. So maybe 7.25. Because again, anything under the x-axis gets counted in a negative fashion. I would say there's about an area of 1 under the x-axis between 4 and 6. And that's all we're adding for G of 6. Now what about G of 8? That's the definite integral from 0 to 8 of f of t dt. Now we know from 0 to 6 we are estimating to be about 7.25. Now it's still negative. Now how much area do you think we're adding from 6 to 8? Looks like 1, 2, 3, almost 3 full squares plus another one. So I would say 1, 2, probably there's about 2 3/4 and there's 1/4. So I would say about 3. So, but that 3 is going to be negative. So I would subtract it, or we do need to subtract it. So that would be, what, 4.25, approximately. Okay? So again, these are just estimates of the accumulation function, which are these integrals. That's what the accumulation, and the reason I wrote the integrals here is because to show you how the accumulation function works. Normally, I would just say g of 8 and figure it out real fast. But I wanted to show you how the accumulation function g is the definite integral with a set left-hand endpoint of 0 and a right-hand endpoint, right-hand limit of integration that is changing. Now let's see here. What does part B say? Part B says find the largest open interval on which g is increasing, and also find the largest interval on which g is decreasing. So, okay, g is our accumulation function. Okay, so let's think about graphing that. So g, don't get confused with f, g is our accumulation function. So let's think about it. Okay, so let's just say x and y. Think about what's happening with g. G of 0 was 0. G of 2 we said was about 6.75. So let's put some scale here. What are our values? Let's count by ones. So 1, 2, 3, 4, 5, 6, 7, 8. And let's count by, let's see again, I guess that's fine. 1, 2, 3, 4, 5, 6, 7, 8. So we have 0, 0. Then we have g of 2 equals 6.75. So 1, 2, 3, 4, 5, 6.75, maybe about like that. Then we have g of 4 is 8.25. So 1, 2, 3, 4, 5, 6, 7, 8 was the highest we went. 1, 2, 3, 4, maybe about right there. And then we have, let's see, g of 6 was 7.25. So 1, 2, 3, 4, 5, 6. Notice now the function has gone down. And then we have g of 8 is 4.25. So what do you notice? If we graph the function increasing, increasing, oh, now we're decreasing. Now where did that change start? We increased up until we got to what? A g of 4. Now why does that make sense? Because we're adding area, because the area under the curve is positive until we get to 4. After 4, we start subtracting, and so the function g goes down. So we would say we're increasing from 0 to 4, and then we're decreasing from, 4 to 8 as far as this function is concerned. From the picture we have, 4, oh, not infinity, 4 to 8. Okay? Because after 4, we start subtracting area from g, subtracting from g. So we're getting bigger, bigger, bigger. Notice our value is 0, 6.75, 8.25. But then we start subtracting area when we go beyond 6, and it's getting smaller. So what about extrema? This is like a chapter, chapter 4 question. There is a what? Local max. I mean, if this is our entire function, then it's a global max. But if this is all we have to go off of, then that's going to be a global max. We'll just call it a local max. Because remember, what happens when you change from increasing to decreasing? That's when you have a local max. And there is a rough sketch. Okay? Again, no graph paper. It's not perfect, but you can see that we're accumulating. The area is getting bigger, 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 bigger. Then our function f dips below the x-axis, so the area reaches a peak, and then the area is being subtracted from, and so area goes down, which results in a local max at that point, and there's a rough sketch of the picture. One more example. I know this has been a long lecture. We're at about 2.5 hours or so, but again, this is one of the most important sections of the book, especially of Chapter 5, and especially of the Calc 1 first semester course. Last example, and then we're going to call it a day, because it's time for lunch. Let me draw a picture, then we're going to answer some questions about a picture. Give me just a moment, and I will sketch this. All right, so I want to just do a nice curvy picture here. Let's do something like this, like so. And we are going to label this as region A, and this is region B. And I'm going to give us a few pieces of information to go on. And that is going to be region A. A has an area of 1.5. Okay? And we're going to be told that we need to put some scale here. Let's say that is 2 and that is 6, and of course that's the origin 0. And we are going to be also told that the definite integral from 0 to 6 of f of x dx equals 3.5, and of course I should probably label this. Of course the blue curve is f of x. Now I want to ask and answer questions about this graph. So notice I underlined here, A has an area. Now we need to make the distinction. Area, as far as just area of an object is concerned, is always positive. If I say what's the area of a triangle, it's a positive or at least a non-negative number. Area of a rectangle is a non-negative number. Okay, but as far as an integral goes, if we looked at the integral from 0 to 2, it would be a negative number. We say the area counts in a negative way. You know, I'm kind of loose with when I say the area is negative. What I mean is the portion below the x-axis counts in a negative fashion, because area itself is always a non-negative quantity. You know, like I said, the area of a rectangle is, you can't say is -5. Okay, but we can say that since a region is below the x-axis, the integral is negative. But we would never say area itself is negative. Now, the reason I'm doing this example is to stress these terms. So let's see. Let's look at a couple examples. Let us look at, let's see, first of all, the integral from 0 to 2 of f of x dx. Now, all we're told is that section A has an area of 1.5 and that the entire integral is 3.5. So what do you think about the definite integral from 0 to 2? Okay, now here's what we have to make the distinction, just like I was just mentioning. If the section A has an area of 1.5 and that section happens to be below the x-axis, then the definite integral has to be equal to -1.5 because the area below the x-axis counts in a negative fashion. Remember, net area means you take the area below the x-axis, subtract it, area above the x-axis, and add it. But now from 0 to 2, everything is below the x-axis. So since the entire section, the entire region is below the x-axis, that entire 1.5 is, for the integral, is negative. So the area is positive, but the integral, the definite integral, is negative. What about, let's see. So that was first. What about the integral from 2 to 6 of f of x dx? Okay. Now, we aren't told anything specifically about 2 to 6 in our givens over here, but I think if we use the properties of indefinite integrals, we can figure this out. Because what are we told? We are told that by properties of definite integrals, we could say what? We could say that this would be equal to the integral from 0 to 6 of f of x dx, which we know, minus the integral from 0 to 2 of f of x dx. Now, why would that be true? Think about if I added this quantity to both sides of the equation. If I added this quantity to both sides of the equation, I would have integral 0 to 2 f of x dx plus the integral from 2 to 6 of f of x dx equals the integral from 0 to 6 of f of x dx. Isn't that an exact application of one of our properties of definite integrals we talked about in a previous lesson? So again, this exercise is going to force us to really go back to our properties of definite integrals and this notion of when area is counted in a positive fashion versus a negative fashion. Now, okay, so now I know what this is. So I rewrote this in terms of two things that I know what they are. I know I'm given that the definite integral from 0 to 6 is 3.5. And I know what this is. From 0 to 2, I just found that out in the previous exercise. So minus negative 1.5. So equals, let's see, 3.5 plus 1.5, that is 5. Okay? So again, we're applying the properties of definite integrals and considering what area means as far as being above or below the x-axis. Essentially, we're exploring the idea of net area. What about the next one? What about 0 to 6 of the absolute value of f of x dx? Now, we just talked about absolute value, right? What does absolute value do? Absolute value takes any portion that was below the x-axis and flips it above the x-axis. It reflects it. So, whereas the integral here was negative, when we reflect it because of absolute value, it's going to make it positive. So a technical application would be, we would take the integral from 0 to 2 and say this is equal to absolute value of f of x from 0 to 2 dx plus the integral from 2 to 6 absolute value of f of x dx. Now here's the thing. We would notice that we're going to take the flip it. Now how do you flip across the x-axis? You introduce a negative sign. Now what does absolute value say? Same thing. Absolute value says if this is known to be negative, simply negate it and you'll make it positive. So this is equal to, algebraically, 0 to 2 of negative f of x dx plus the definite integral from, nope, not 0, 2 to 6. Now, what does absolute value do if your item is already known to be positive or non-negative? It doesn't do anything. So that's just equal to the integral from 2 to 6 of f of x. Now, this we can factor out that negative sign because it's a constant. Put the negative sign right there. And now what's the integral from 0 to 2 of f of x dx? It's negative 1.5, which we have negative 1.5. Now what is the integral from 2 to 6? We just found that to be equal to 5. So plus 5. And now we have negative 1.5 plus 5, so that is 6.5. Okay? So the total area and the absolute value gives you, imagine what absolute value does is it flips this portion above the x-axis. So absolute value is looking for this area and this area. That's what absolute value does. Okay? Takes everything and makes it positive. The region over here, B, was already positive, but we had to flip region A and make it positive. That is, take the opposite of it. A couple more here. Let's see. Let's look at the integral from 0 to 2 of negative 2 times f of x dx. Now this should be an easy one, right? Because we know immediately we can factor a negative 2 out and say integral from 0 to 2 f of x dx. Now negative 2, now what do we know the integral from 0 to 2 is? We know it's negative 1.5. So negative 1.5 times negative 2, we get positive 3. Okay. Let us see. What about 0 to 6? I like these because it makes you think. It catches a lot of students off guard. 2 plus f of x dx. This usually really throws students off because we have a 2 all of a sudden. We don't know anything about 2. Well, let's just think. By the rules of integrals, we have properties of integrals. We have 0 to 6. That's integral of 2 dx plus the definite integral from 0 to 6 of f of x dx. Now, how we integrate 2, that's easy. That's just 2x from 0 to 6. That's just a fundamental theorem of calculus problem. Plus, what do we know this is already from a previous step? We know that the integral from 0 to 6 was, we're told, directions, 3.5. So what is this? Well, it's just what? 12 minus 0. So 12 plus 3.5 equals 15.5. Okay. What about, let's see here. Let's mix it up a little bit. What about the, here, let's change colors since we're going to be kind of cramped here. What about, 2 to 0? Well, actually, let's do this. What about from 6 to 2 of f of x dx? Well, what do we know we can do here? We can put a negative sign out front and then flip the limits of integration 2 to 6 f of x dx. Now, what is 2 to 6? We found was 5. So negative 5. Remember, if we transpose the limits of integration, we can do so and just simply add a negative sign in front, and we know once we transpose those limits of integration, we get 2 to 6, which we know the answer is already, it's 5. So negative 5 is that. We're integrating backwards, essentially, from 6 to 2. We're going backwards in integration. Here's an interesting question. How do you find the average value? Remember, the average value, f of c, equals, this is the mean value theorem, 1 over b minus a times the integral from a to b of f of x dx. Well, what's b minus a? It's b is 6, a is, the lowercase a is your left-hand point of the interval. So 0 to 6, so you have 1 over 6 times the integral from a to b, so 0 to 6. What's the integral from 0 to 6? Oh, we found that right. Oh, that was easy. We're told the integral. It's 0 to 6, 3.5. So what's 3.5 divided by 6? So the average value is 7 over 12. So that's what the mean value theorem tells us. So what's interesting about that? Again, what's really cool about that is that you can draw a rectangle. Let's see here. Let's make this rectangle. Pink is fine, I suppose. Let's erase all that. You can draw a rectangle where the base of that rectangle is the width of the interval. So the base of the rectangle is going to be 0 to 6, and the height of the rectangle is 7 over 12. Now, we don't really have a scale here. We know that's 6, so that's a distance of 6. 7 over 12 is like a half. So it's going to be a pretty short rectangle. But we can draw a rectangle like so, such that the area of this rectangle is equal to the net area, which I suppose I'll shade that in orange. The net area is all of this. But remember, the stuff above the x-axis counts in a positive way, and this region below the x-axis counts in a negative way. So if you take region B, subtract off region A, B minus A, that number equals the same number as the pink shaded area, which in this case we know is it's 7 over 12. 7 over 12 times 6, which gives you 3.5 is the area of that pink rectangle. So the area of the pink rectangle is equal to 3.5. The height of the pink rectangle is 7 over 12. 7 over 12 is the average value, and that again is according to the mean value theorem right here, which is guaranteed to be on a test if you're in a Calc 1 or in case you're in a Calc 2 class where this comes about. Guaranteed to be on a test. Mean value theorem for integrals is a pretty important concept. So I think that is about all I wanted to cover. We've covered, let's just recap. Let's scroll all the way back up to the top. It's been a while. I think this is a record as far as these lectures are concerned. But we had the Fundamental Theorem of Calculus, probably the most important result we've had in a while, if not the entire course. It allows us to find a definite integral in a much easier way than we had previously. Previously, we were stuck with geometry or Riemann sums. Fundamental Theorem of Calculus, again, we call this Part 1, or the first Fundamental Theorem of Calculus, was awesome because it made definite integrals way easier to find. We then had the mean value theorem. The mean value theorem allows us to find the average y value of a function over a given interval. It also allows us to find a rectangle such that the rectangle has the same area equal to the definite integral over AB. We had the second fundamental theorem of calculus. It essentially guaranteed that if a function is continuous over a certain interval, then we're guaranteed an antiderivative. Once we find that antiderivative, if we take its derivative, you get the original function, and that's, practically was pretty nice about the fundamental theorem of calculus is that we could take the derivative of hard definite integrals and get a solution pretty easily. We then talked about the net change theorem. Essentially, it's just a restatement of the fundamental theorem of calculus part 1, but it stresses the fact that you're taking the definite integral of a rate of change, and so we talk about net change, much like we talk about net area. We talk about velocity versus velocity. If you're taking the definite integral of a velocity function, and how If you take, very important, if you take the definite integral of an absolute value of velocity, the result, the interpretation is total distance traveled. But if you take the definite integral of just a plain velocity function, no absolute value, then your interpretation of your solution is displacement. Displacement and total distance traveled equal each other if your velocity function is non-negative over your time interval in question. Otherwise, total distance traveled is going to be a bigger quantity. All right, that about wraps it up. Okay, we have one more lecture to go in this semester. It will be over what's called U substitution. It'll essentially be, the U substitution will allow us to take the antiderivative of more types of functions. Kind of like the chain rule will allow us to take the derivative of lots of new types of functions, composition specifically. Thus far, we haven't dealt with any composition of functions, and the U substitution is a technique that will allow us to deal with composition of functions. So not a lot of new theorems in 5.5. 5.5 is a pretty tough section, but we don't really have any new theorems to worry about. It's just a new technique of how to, well, I guess there is one or two theorems, but it's really about how, it's really techniques for how to integrate functions when you have composition. So there's a preview of what we're doing next. If you have any questions, always feel free to ask. See you soon. Good luck.